Plasma powers the sun, creates the aurora, and fills the space between the planets. It is the most common state of matter in the universe, and for the Navy, understanding it can mean protecting satellites, strengthening communications, and creating entirely new capabilities. For 60 years, scientists at the U.S. Naval Research Laboratory have worked to understand plasma and harness its potential for the fleet and the nation. In 1966, at the height of the Cold War, NRL brought together researchers studying magnetic fusion, space plasma physics, nuclear effects, and intense light and particle beams. Their mission was ambitious: understand plasma and put that knowledge to work.
The division was established in 1966 by Dr. Alan Kolb. The division had about 32 employees at its beginning. It was formed with the mission of trying to understand how you confine a plasma at fusion conditions. Today we have a workforce of about 100 scientists, engineers, and support staff in 4 branches that executes a broad research portfolio. That portfolio includes understanding space weather to assure Navy and commercial operations in space, simulating nuclear weapons effects to test military materials and components, plasma processing to develop advanced materials, next generation directed energy science and technology, and realizing practical fusion energy.
One of the division's earliest challenges was understanding the electrically charged environment surrounding Earth. Solar activity can disturb that environment, threatening systems that military and civilian operations depend on every day.
When solar storms happen and the solar wind impacts the Earth, it can create varying conditions. Similar to storms that happen on the Earth, we can have storms that happen in space, and we have to be prepared for that to keep constant operation of our satellites. We've created a number of large plasma devices, and we generate plasmas with various sources that mimic the conditions that you find in space. And then we can use our diagnostics on the ground to conduct reproducible experiments to study these phenomena and understand the basic physics that's at work in the harsh space environment.
That research can even help reveal objects too small to see easily from the ground.
Since the dawn of the space age, we have been leaving a lot of debris in space. Smaller debris are very difficult to optically track and detect. And the debris gets charged naturally in space. But this charged debris, when it speeds through the ambient plasma of space, creates an interaction which nonlinearly creates states that are long-lived. These states can be detected by radar and other detectors. They actually amplify the size of the debris effectively, and then it becomes easier to track.
Plasma also gives scientists a way to investigate matter under extreme conditions. NRL's post-power facilities and high-energy radiation sources support strategic systems, advanced diagnostics, and fundamental research that cannot be reproduced anywhere else.
The experimental facilities give us the ability to have our scientists in the laboratory turning wrenches, setting up experiments, buying equipment, knowing what works, what doesn't work. Our theorists can walk right next door and see the data being made immediately and get validation data for the codes. Everyone says you can simulate everything. The ground truth is in the experiments. The experiments may not have the perfect diagnostics, but they have the perfect physics. I've always liked to call us a university with a fence. So we can go from the crazy idea at the low technology readiness level and take it all the way and transition it to the fleet.
That ability to move from fundamental science to operational technology has helped transform directed energy. By understanding how intense beams interact with the atmosphere, materials, and plasma, NRL is advancing systems for missions ranging from remote sensing to defense against emerging threats.
These sorts of systems could solve problems like blinding or spoofing enemy sensors, defeating unmanned aerial systems, defending against missile threats, as well as a whole host of other potential applications in directed energy and remote sensing.
But plasma innovation is not limited to space or defense. It is also changing how advanced materials and microelectronics are manufactured, one atomic layer at a time.
Labs turned out to be a really interesting project. Initially, it was developed to be a large area etching tool, which was to address a need at the late 1990s when they were scaling up plasma processing tools in the semiconductor industry. It turned out, however, that Labs had a number of very unique features that turned out to be sort of ahead of its time. One of those was the ability to finally control the ion energy at surfaces, and the other was to be able to carefully control the amount or density of reactive species in the plasma. Both those attributes turned out to be very important for atomic layer processing and is now a commercial process, and it's used to produce some of the next generation devices, either electronic or sensing, that are useful in both the semiconductor industry and also to the Department of Defense.
NRL's plasma legacy also reaches toward one of science's most enduring goals, harnessing fusion, the same process that powers the stars.
So NRL has been involved in fusion research for more than 6 decades, and there's a lot of seminal results that have come out of NRL in various associated sub-disciplines, including inertial confinement fusion, laser plasma instabilities, pulse power science, advanced plasma diagnostics, and computational methods. So among the various innovations, I would say, that NRL has produced, the first flash lamp pumped glass disc amplifiers for high energy glass lasers. This is the technology that's presently used, for example, in the National Ignition Facility, which recently demonstrated ignition on a fusion target. Closer to home, facilities like this, the Nike laser, also helped to advance laser-driven fusion and contributed to important technologies like beam smoothing that continue to shape and influence fusion research worldwide.
After 6 decades, the technologies have changed, but the division's purpose remains the same: pursue difficult science, discover what is possible, and turn that knowledge into capability.
Plasma research at NRL has always been about pushing the boundaries of physics to solve real-world problems in service to the Navy and the nation. This is our 60-year legacy, and we look forward to continuing this for the next 60 or more years.
For 60 years, NRL's Plasma Physics Division has transformed scientific curiosity into technological innovation, and innovation into capability. Its next discovery may shape the next 60 years.